All right, we're back for Nucleophilic Substitution Part 2. If you have not watched Nucleophilic Substitution Part 1, I would strongly suggest you go and do that. Okay, so there's one thing that I forgot to mention when we were talking about rearrangement. We can do it with hydrogen. We can also do it with a methyl group. So let's say that I have this cool little benzene ring here, and it's got some stuff hanging off of it. And this bromine is going to kick itself out, and we're going to get a carbocation. I know what you're thinking. It's going to be a primary carbocation. Oh, it's going to be so bad and so unstable. But we have a trick up our sleeve. And that trick is called a methyl shift. And I just drew one too many carbons. So we're going to back it up. There's a plus here. Okay, so the methyl shift works like this whole carbon. I'm going to draw it as a CH3. So this is a CH3. This carbon is going to pack up its electrons from the bond, and it's going to move over here. And it can only do that if it's next door, if it's right next to it, that carbon. So now we're going to get something that looks like this. And this has a whole bunch of resonance structures. So I can, for example, move these electrons here, and I can get this. Or I can move, what'd I do? These electrons here, and then I can get another plus, right? So this is in resonance with this. And I can keep doing that. I can chase this carbocation around the benzene ring until I'm really exhausted of drawing these structures. But I hope you get the point that now this is stable because we shifted over the methyl group. So we can do this kind of rearrangement with hydrogens, with methyl groups, and only to the carbons that are adjacent. So there's one other interesting thing that I want to show you before we move on to some practice problems, and that is how we get an OH group off. So that's often going to happen is you're going to have an alcohol. So maybe it looks like this, right? And we want to substitute this OH group for something else, except that OH is a really, really good nucleophile, right? OH minus, amazing nucleophile. That means it's a really bad leaving group. It doesn't like to leave. So we have to kind of do something to it to make it a more stable leaving group, and then it can get out of there. So there's a couple different things we can do to make OH a better leaving group, and they all involve like these big kind of crazy molecules that will help spread out electron density for that oxygen. So one of them is called a tosylate or a tosyl group, and it looks like this. So you see all those double bonds, that's going to create a ton of resonance structures to delocalize the negative charge when we get the oxygen to leave with this group. So often you're going to see it as a tosyl chloride, so that's where you have chlorine here. And this whole thing gets abbreviated TS. So this you might see as TSCl. And what's going to happen is that this oxygen, it's got two lone pairs, right? So it's going to grab on to this sulfur in here, and this chlorine is going to get out. Sometimes there's an intermediate step you can draw where first one of these bonds gets onto the oxygen, and then that new like O minus has another pair of electrons, and that can get kicked back in, and then the chlorine gets kicked out. But we're just going to draw it like this. Out comes the chlorine. And then this is going to make OH, and we're going to abbreviate that whole group TS. And we have a chlorine that's now negative. Now we have a negative, we have to have a positive somewhere, and that positive is going to go in the oxygen. Whenever oxygen has 3 bonds, it's positive. So now it's going to be easy for it to leave because it's going to leave and it's going to become neutral. So when we use a tosyl chloride, the chlorine becomes the nucleophile. So here comes the chlorine with its electrons, and it's going to kick out this whole entire group. And that's going to get us our product. And we have this kind of side thing of HODS. I hope that makes sense because we're going to go into something similar again. So another thing that's kind of like that is called thionyl chloride. So let's make a simpler reactant. Let's just do isopropyl alcohol. And thionyl chloride looks like this. So thionyl comes from the fact that it's a sulfur. Thiol is SH, so thionyl kind of makes sense that it has sulfur in it. And chloride comes from the chlorines. So this is going to be kind of the same principle. So here I am going to show this double bond displacement thing, and this is going to happen a lot later on in your organic chemistry career, I guess I would call it. But that's going to happen a lot with carbonyls, which are C double bonded to O. So this thionyl, what's going to happen is this goes in, gets the sulfur, and this is the part I kind of skipped over with the tosylate, is that one of these double bonds gets kicked out, and you're going to get this thing, this big kind of crazy complex. Oxygen is positive, and you have your sulfur here, and now you have an O minus. It's got an extra lone pair on it. So before it had 2 lone pairs, now it's got 3 and a minus, and we still have 2 chlorines. And now this oxygen is going to kick back in its electrons into that double bond, and sulfur is going to say I have too many things, and one of the chlorines is going to have to go. And this gets us this. Also, nice double bonds, good for resonance, right? And we have a positive here, and we have our negative chlorine. And our negative chlorine is going to come in here, and it's going to kick out this whole group. And this group doesn't have an abbreviation like TS. We just draw the whole thing. So we have this, and we have this. And these are our products. There's one more that I want to show you, and this one is called PBr3, or phosphorus tribromide. So if we take our same OH, we have a phosphorus, and it's got 3 bromines around it, and a lone pair. So this oxygen is going to attack the phosphorus, which, like those sulfurs that we've been seeing get attacked, this is a partial positive in here. And remember that this oxygen is partial negative. So this is going to attack in here. There's no double bonds that we can kick out like we did with the sulfur double bonded to oxygen. So this is going to be one simple step. We have this bromine get kicked out. And you guessed it, bromine is now going to be our nucleophile. So bromine comes on in, and it's going to kick out this whole group. And then we will get our product that looks like this, and this weird little side thingy that looks like this. So that's how to get an oxygen off of something. And these are, I think they can be used for SN1 and SN2. I've seen them more in SN2. Because for SN1, you can use an acid, and you can have, you can basically protonate the alcohol and have a basically a water hanging off, and then you can get that water out. So we can do one of those actually. So if we have, this is going to be an SN1 now. We have an OH, and we're floating around in a protic solvent because we're SN1, and this protic solvent looks like this. It's ethanol. Except that we are going to have an acid in our solution. So this ethanol is going to get protonated, and it's going to be positive. So if we want to sub in our ethanol for our current OH group and make an ether, oops, that's the wrong arrow, definitely the wrong arrow. We are going to have this OH act like a base. It's going to take off this hydrogen. These electrons are going to go back to the alcohol. So the alcohol is going to be neutral now. And I mean, they're both alcohols. The ethanol is going to be neutral now, and this isopropyl alcohol is going to be positive with 2 hydrogens on it. So now what can happen is we can just kick out this water that's happy to go off on its own, a lot happier than the OH. And now we have a positive thing. And I forgot, here we have our ethanol without an extra proton as a product in that one. But now we have water and a carbocation. So now our ethanol can come in. And it's a weak nucleophile because it's got a partial negative here with its little lone pairs of electrons. And it can come in and we can get this. Right, so this is our ethanol. And we now have a water or another ethanol. It doesn't matter which one it is, but I'm going to say it's another ethanol floating around, right? Because we have millions of these things floating around. And it's going to act like a base, and it's going to take this hydrogen, and these electrons are going to go back and make our new product, our ether, neutral. So this is what we call regenerating a catalyst. So now we got back this thing we had in the beginning, and all that this is doing is making the reaction a little easier and a little faster. That's what a catalyst does. And we have our product that looks like this. And that's an ether because we have carbon stuff on either side of this oxygen. So I hope that makes sense. That's all I have to say on the subjects of SN1 and SN2. So we can do some practice problems. So let's say that I have this substrate here. And we have this nucleophile. And it's in this solvent. So is it SN1 or SN2? Think about it for a moment. Okay, this carbon here, how many carbons is it bonded to? It's bonded to one other carbon. That makes it primary. Primary does not go in SN1. So we know off the bat it's SN2. But if we wanted more evidence, we can look at our nucleophile. Is this strong or weak? Well, any form of nitrogen, like an amine or ammonia, which this is ammonia, it's going to be a pretty strong nucleophile, so we classify this as strong. And acetone, what kind of a solvent is acetone? Acetone is aprotic. Right, because it looks like this. No OH or NH or FH, but we're not going to see FH. Okay, so strong nucleophile and aprotic solvent both go for SN2. So in conclusion, this is SN2. Let's try another one. So this is our new one. This is our new substrate. And this is our solvent. And it's our nucleophile. So this process we're going to call solvolysis. So that's the name of this kind of reaction, where the solvent is also the nucleophile that's subbing in. Solvent, lysis, breaking up. If you want to do anything in biology and anything in chemistry, know that lysis means breaking. It saves your life. Solvolysis, hydrolysis, lysosome, all of that we can get from the word root. Anyways, so because this would have a lot of resonance structures. For our carbocation, we don't care that it's primary. We care that it has a lot of resonance. So, I mean, technically it could go either way, right? Because it could be stable in SN1, and it could be also not sterically hindered in SN2. So actually, I'm not going to cross out that primary just yet. We're going to keep that there. What about this? Is it a strong nucleophile or is it a weak nucleophile? Well, it's not charged. It's an alcohol. Alcohols are pretty much weak nucleophiles, as is water. So this is weak. And is it protic or aprotic? It is protic because it has an OH. So both these things go for SN1. So even though we didn't really know what was going on with the substrate, we know what's going on with the solvent and the nucleophile. So this is SN1. And actually, any time that you see the word solvolysis, it also implies SN1 because basically any solvent that's also a nucleophile is going to be a weak nucleophile. So it's going to be like alcohols and stuff like that. Let's do one more example. And our solvent will be DMSO, and our nucleophile is going to be methanol. Okay, what kind of substitution is this? Well, let's look at the carbons first. What kind of carbon do we have here? How many carbons is it bonded to? It's bonded to this one. So this is primary. And we also, though, have a possibility for if it is SN1, and I'm not saying it's SN1, if it is SN1, we can rearrange, right? We can do a hydride shift over to this neighboring carbon. This neighboring carbon is bonded to 3 other carbons. So this one is tertiary. So we might be able to rearrange. So we have to take that into consideration. Okay, our solvent. It's DMSO. Is it protic or aprotic? Aprotic, because DMSO looks like this. Not carbon. It's a sulfur. What am I talking about? Dimethyl sulf oxide. So that's not protic. It does not have an OH or an NH or an FH. Okay, so then we have our nucleophile, and our nucleophile is an alcohol. Alcohols are weak nucleophiles. So this is weak. So this makes us think SN2, right? This makes us think SN1. And our carbons, they're kind of a toss-up. So with this one, the answer is we don't know. We have to try it out and see.